So it's fun to be here for the Distinguished Alumni Series. The Alumni Office claims you the first day you put your foot on campus. My dad is 95 and has Alzheimer's, and he doesn't know where North Carolina is anymore, but he still has his sense of humor. So I told him I was invited to give this Distinguished Alumni lecture, and without missing a beat, he smirked at me and he said, "So who are you replacing?" So this is a engineering talk, even though this isn't an engineering campus, so I brought my engineer's hat. And I'm going to talk about data center computers. My reading is that the industry is starting to bifurcate, and there's cell phones and there's data centers, and the stuff in the middle is going to drop out a lot. And I want to tell you a bit about data center computers and how they differ quite a bit from desktops. And I want to try to draw some vivid pictures of computing in data centers and expose some ongoing research problems and perhaps inspire some of the students here to contribute in this area, because I think it's going to be pretty important for a while. I want to mention in passing, it was really hard to find a picture of a woman with a light bulb instead of a man. So a little analogy, here's a California ranch house and an apartment building. The analogy is those relate to each other about the same way that a desktop computer relates to what? Data center. Lots of sharing, lots of interactions, lots of congestion, lots of different agendas. The whole works. So I'm going to talk about 4 areas where I think data center computers are different from desktops. Moving data, big and small. We find something on the order of 1/4 of all of our server time is spent moving data, memcopy, or Stirland, just finding the end of the length of a string of data, or send message and receive message, which really have an embedded copy inside of them, moving data from network out of the kernel and into the user or whatever. So I'm going to talk a lot of the time about moving data. And then some about what's really going on when you've got thousands of transactions per second and how that's different from running 2 desktop programs. Talk a little bit about isolation between programs. This is an area where we actually need more hardware help in the industry. And then one of my favorite things, talking about measurement underpinnings. So here's data, big and small. In our servers, we're moving data from disk to RAM, from network to RAM, from SSD to RAM, and also a whole lot of just physically putting pieces of data together, juxtaposition. And some of that is bulk data, send a megabyte here and there. But some of it is just little short variable length items. We store Unicode in the UTF-8 encoding, which is a variable length encoding covering all the alphabets in Unicode. And there's some 1-byte characters, some 2 bytes, some 3 bytes, some 4 byte. And when you're putting those together, you're moving little tiny bits of data. And it's really bad if you have to do like this 4-way branch. It says, go here and move 1 byte, go here, move 2 bytes, move here. Because the conditional branches are always slowing you down. Or you're putting together packets and there's, this header and that header and this VLAN tag and this other stuff and this checksum. And it's all physically put it together and then send it. We also do a lot of compressing and decompressing, and there's lots of data movement involved in those. And the decompressing is fundamentally picking up little pieces of a big file and putting them back together in the order they started out in. And then we do checksumming. Everything we write on disk is checksummed in software in addition to all of the hardware stuff, because otherwise we lose data. And so we're just taking passes over stuff. I looked at one of our disk servers and counted. And to read a block off disk, every byte of that block was actually touched in memory 11 times. So processors, the 4004 had no memory. More recent things like the Intel i7 have like 12 megabytes of cache on them. But when you look at a data center server, it's really this big dinosaur where everything is memory. And then there's a little bit of processor. And the connection between them is pretty puny. And if you look at where the money goes, the money doesn't go into the processor chip. It goes into lots and lots of RAM. 64 gigabytes, even up to a terabyte. You're talking massive amounts of RAM, which has a strong consequence. If you have a lot of RAM and you actually paid for it, it means you want to use it. You want to put stuff into it and you want to get stuff out of it. And we will see in a little while what that means is caches don't work because you've got way too much RAM compared to the cache sizes. So this is sort of an odd environment. I'm going to go through a little bit of a hypothetical cache structure and then go through some of the problems. So just quickly, pretend you've got a 64-core machine, which is 16 physical cores, each of which has like 4 PCs, so hyper-threaded, whatever. And that each of the physical cores has its own level 1 cache, and a bunch of those, maybe 4 of those, share a level 2 cache, and all of them share something like a level 3 cache, and then there's a bunch of DRAMs. So this is sort of a generalization of the kinds of things you can actually buy today. And I'm going to take, as a forcing function, I'm going to talk about this forcing function for about the next 10 or 12 minutes. If I wanted to move 16 bytes every cycle, because 25% of my time is doing that, what are the real consequences? What does that mean for the hardware design? That one simple phrase, 16 bytes every cycle, if you take it as an honest statement, what it is you have to build. And I was astounded when I went through what you have to build. First, you need to have something in a load store kind of machine where you load 16 bytes and store 16 bytes and test if you're done and do a conditional branch every cycle. So just for starters, you need a 4-way issue machine in order to hit the goal. And you also need some 16-byte registers, but everybody has those. And if you look at today's sort of processor speeds at 3 gigahertz per second, times 16, you're up to 50 gigabytes per second of read traffic. And another 50 gigabytes per second of write traffic. And that means you need to be hitting the first level caches with a total of 100 gigabytes per second. Every cycle, all the time, every second for many seconds in a row. And if you mess up, and in fact, if you buy any of today's machines, you're actually talking 150 gigabytes per second because the stream that you're writing, every cache line is actually read first, completely overwritten, so the read is a total waste of time, and then written back to RAM. So there's a factor 1.5 loss in data movement in every processor chip you can buy today, which is unfortunate from my point of view. So here's a little bit on short strings where we're doing packet pieces or words or web pages or things. So there's just lots of little pieces. And I think I skipped a slide there. Excuse me a second. There, okay. And if you look at things like that in 16-byte chunks, if we want to move short stuff at the rate of about 16 bytes per cycle, that means you need to pick up most of 16 bytes, and on the very next cycle, the next chunk, and on the very next cycle, the next chunk. And if you look at something like the memcopy code, it spends a whole bunch of time up front trying to figure out what to do and what the length is and stuff, and you don't get to the first move until about 8 cycles later. That's great if you're moving a megabyte. It's no good if you're going to move 4 bytes and get out. You're spending 2/3 of the time in the overhead. And if you look at this stuff instead of as little pieces as aligned cache lines, oh no, things don't line up right. I get a few bytes here, but I need to shift them over a little bit and bring in 2 more characters from there, 2 more bytes from there in order to do that, which means if I'm going to move 16 bytes per cycle and the target and the source are not aligned to the same 16-byte boundary, it means I need to pick up some chunks and I need to shift and I need to store them away, and I need to do that picking up and shifting and storing all in one cycle, pipelined in some way. So it will turn out to have a shift in a 16-byte register machine that takes 2 16-byte registers, shifts the whole works, and pulls out 16 bytes. If you don't have that, you can't move 16 bytes every cycle. And you can't buy that today either. So this has turned out to be a nice forcing function. I believe in terms of instruction sets, it would be well worthwhile for the CPU vendors, and perhaps some of the students here will become employees of CPU vendors, to have a load partial instruction and a store partial instruction that all you do is you give it an address and a length, and it loads 0 to 15 bytes from that address, or stores 0 to 15 bytes to that address in one cycle. And this is stuff that's easy to do in the hardware path because the connection paths are already there for unaligned loads. Picking off the low 4 bits of the length is easy. But if you do it in software, you're doing a bunch of anding and branching, and it's slow. And you can get the load instruction in the IBM Power series, except that it loads 4-byte registers up to 8 of them, and so it's actually 4 bytes per cycle, and takes a bunch of cycles, and it's a very messy instruction. And you can actually get the store partial in the Itanium, but you can't buy anything that does both of these in one cycle each. If you had that, all of these short moves just become load store, and you're done. There's no branching. So I'm going to go back now and look at the next consequence of moving a bunch of stuff. So I've got a data cache, I've got some loads and stores. This cache, in addition to I'm reading 50 gigabytes per second into this processor and writing 50 gigabytes per second, the backside of this cache also has to be moving a total of 100 gigabytes per second, filling and writing back. And the backside of the L2 cache has to be moving 100 gigabytes per second, and the RAM system has to be doing that. And if I'm sharing this L2 with other cores, it's like, oh, do I have to multiply by 16? And all of these cores are doing it all at once? Well, fortunately, you don't. If about a fourth of the total server time is spent moving data, if we had 4 of the 16 cores really running flat out moving data, the others could be doing other stuff, and that would be okay. So instead of 100 gigabytes per second times 16 down here, actually 100 gigabytes per second times 4 would be a fairly good balance. So this idea of I can get to the L1 cache and back, manufacturers are really happy to talk to you about. They're not as happy to talk about the sustained bandwidth all the way through, and the sustained bandwidth while other processors are doing anything whatsoever. But again, it's just I want to move 16 bytes per second. What do you need to do that? If you can do that, you end up with a single processor chip that is in the top 20 of the stream copy bandwidth from last April, 400 gigabytes per second. It's a little slower than some of these SGI machines, a little faster than this Oracle Sun things, all of which are built with lots of processors instead of just one CPU chip. So as an industry, the high-end data center processor vendors haven't really focused on what a bottleneck this is. Then there's the next step. If you get 256 gigabytes of RAM, as I said earlier, it's only worth buying it if you're going to use it. If you fill it up with lots of stuff, that means that if you've got 50 or 20 gigabytes of cache, almost everything you're accessing is not in the cache. And main memory on any of these machines is optimistically 200 cycles away. Pessimistically, in the real world, it may be 500 or 600 cycles away. But I'm going to stick with 200. So I'm going to walk you through, in the next 2 slides, a cycle by cycle at 4 hertz of load, add, store, all cache hits, and then do it again where the second load is a miss. And I want to ask the faculty in particular to be patient during this. When I've given this before, the faculty have interrupted. So this is the load, add, store. Did you all catch that? I'll run it again. Here's the load, add, store at 4 cycles. Now we're going to do it with a cache miss at 200 cycles. That is a cache miss. I want you to internalize how long that is and think about what else you could be doing. That was the optimistic case. The servers we have, cache misses are often 400 cycles. I'm not that patient. That 50 seconds is 2% of this talk, and it's for you to internalize what a cache miss really is. So you're going to have high miss rates. You're going to have stuff that's 200 cycles away. If I really am going to move 16 bytes every cycle, that means I need to be 200 cycles ahead. I need to prefetch at least 3.2 kilobytes if I'm not going to be waiting on cache misses. This is for long moves. So I need like order of 4 kilobytes of prefetching just for this simple, I want to do 16 bytes every cycle, please. You can't buy that today. You can buy one cache block, 64 bytes of prefetch, but you can't buy 4K. But you need to if you're going to be honest about moving that much data that quickly. But there's more, as they would say on late night TV. The L1 cache size in a real machine, the upper limit of the size is the associativity of the cache times the page size. If it's bigger than that, you have to first do the page mapping from virtual to physical and then start the cache lookup, and it takes 2 cycles instead of 1. Or you have to build a virtual cache, which nobody does because the hardware vendors don't have enough control over the operating system vendors to make that actually work, and so they won't build chips that do that. So if you've got a 4K page and an 8-way associative first level cache, it's 32 kilobytes, end of story. That's all you can buy today. Cannot get more. Amdahl 470 was the first place I saw this, of a 2-way associative cache with 4K pages and an 8K cache, and doing the TB lookup in parallel with the cache lookup to find out the next bits. So we really need much bigger than 4K pages. Also, if you have a translation buffer with like 256 entries at 4K each, it's a megabyte. Chips in your laptops probably have 20 megabytes of cache on them. You cannot access even the cache on the chip without taking translation buffer misses. We have data center programs that spend 15% of the time in the TB miss microcode. Those machines would be 15% cheaper if we had bigger pages and spent a lot less time in the TB miss microcode. And finally, if you got 256 gigabytes of RAM at 4K each, you got 64 million pages. That's a little more balls to juggle than you actually need. If you had 1 million pages, life would be good. If you have 1,000 pages, life is a little tough. But 64 million is just a total waste. It's a tough transition for this industry to move to a larger page size, and it will take probably 5 or 10 years, and it will take some of your careers. It took forever to move from 512 byte blocks on disk to 4K. Excuse me. The reason for that was that the first partition allocated by Windows was not an even multiple of 4K. And so if you built a disk that had 4K blocks, everything that the user accessed on a PC would be not aligned on a 4K boundary, and every read would do 2 reads and every write would do 2 writes. And it took 10 years before Windows 7 finally aligned the boot partition on a megabyte boundary so you could have bigger blocks on disks. So it's still all about the memory. I wrote a paper 20 years ago about it's the memory stupid, and it's still the memory. And we need, I think, in the industry, a better coordinated design between instructions and implementations. This is one of these things that sort of crosses the boundary a bit. So the challenges are, for data centers, having lots of memory, having lots of multiple issue, having full bandwidth of the RAM, having prefetching, having bigger pages, and perhaps more, and for you all to think about how can you do better. So that's the first fourth, that's the long fourth. I'm going to talk about real-time transactions. Unlike desktops, we do things with thousands of transactions going on per second. I'm going to walk you through a sequence of 4 views of transactions. So this first one is, each of these is a rack of processors about my width and about my height, and a lot heavier than I am, full of maybe 50, 60 processor boards. And this is a graph of one search query that comes into a machine, and it passes pieces of the search query in yellow out to about 100 other machines, and each of those passes more of the work out in blue to other machines yet. And there's actually a third level that I didn't show because otherwise the whole slide would be black. And this is just one query, and it goes bam, 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 bam. Second level goes bam, 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 bam. All of the third levels do a millisecond or two of work, and then all the answers come back bam, 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 and get merged together on the way back up the tree and get back here in maybe 20 milliseconds. Meanwhile, another 20 to 100 other search queries have been going on this same set of computers at the same time. So life is very busy. This is a slice of the same search query split up in a different way. This is taking the incoming query at the top level and showing on a timeline how long it took before the answer came back, which is out at about 160 milliseconds. Not 10 or 20, it turns out. And within that, this is the call tree of that top level going out to 93 other processors and asking each of them to do a piece of work. And the call tree has a few anomalies in it. First, there's a call off to this other machine. Nothing else happens till that returns. Then there's 93 parallel calls off to lots of other machines. And then this guy is quite a bit slower than the rest, and this guy is slower yet. Okay? And it's the last guy that comes back that determines how long the whole search query for the user takes. So the nice thing about doing lots of parallel computation is you get 100 different machines working on it. In fact, when it spreads out, 2,000 different machines. The bad thing is it's the slowest one that determines the response time. And it turns out one of my peculiar interests is in the 99th percentile latency. The amount of time during which 99% of the responses take less than that time, but 1% take more. So the 1% long delay tail are the kinds of problems I like to look at and understand. If you do 100 things in parallel and you look at the 99th percentile net response, you find that nearly everything is taking the longest time, the 99th percentile time. You know, 1 out of 100, and you do 100 of them, and sure enough, you end up here for every user, for every search, for every transaction. And so controlling the tail turns out to be really important and, in fact, worth a lot of money. So that was a slice across a time call graph of lots of one transaction. This is now in a single server doing one transaction. This is actually a fairly old Gmail delivery. And this is a Gmail delivery that does a bunch of stuff and a bunch of stuff, and these are all different subroutines that run, different procedures that run for the delivery. This is another delivery, a third delivery that's a bit longer, a fourth delivery. And you can see most of these, if we look at the time scale, most of these are like 10 milliseconds each. And then there's this one, this whole bottom thing is I'm sorry, not 10, 60 to 70 milliseconds each. This whole bottom thing is 1,800 milliseconds. 1.8 seconds for a single email delivery. And it starts the same way. And the nice thing about drawing stuff this way, so you have sort of a carriage return at the beginning of each piece, is you get to see what's different about this guy. And it's all this blue stuff. And it turned out this blue stuff was re-indexing the words from these that had just come in and doing it on the same processor thread that was doing the incoming mail rather than doing it on some other thread. This picture caused the early Gmail software designed to change the following week to put this re-indexing on another thread. And it cut the tail latency from 1,800 milliseconds to something more like 100. The point is, it's hard to spot what's going on there if you do something like profiling or whatever, because everything gets merged together. You have to get all of the pieces of individual things and see what's different for the long ones. So I'm going to take another slice of one server. This one we're looking at 4 different CPUs with time going sideways. This is 200 microseconds. And showing in time on each of the CPUs what's running. And the different rectangles in different colors are different programs, or the tall guys, in fact, are kernel calls or interrupt processing. So the medium width, the smallest width stuff, the black lines are the idle job. The medium width stuff are user mode things, the orange or whatever. And the tall little skinny rectangles are kernel mode execution. So what we see here is 200 microseconds, a little more along the top of CPU 0 is always busy, mostly doing this user mode thing, whatever it is, and doing quite a number of small little kernel calls and returns. CPU 1 is mostly idle half the time, but it's doing a fair amount of what turns out to be mostly interrupt processing, and whatever this narrow orange process is. CPU 2 is almost empty except for what turns out to be a timer interrupt, and CPU 3 is completely empty. This is a little bit of network traffic coming in and getting processed. The orange guy here on CPU 1 is actually TCP dump. Every interrupt that comes in with a network packet runs TCP dump and then delivers the packet to the main thread that did the receive message call. And looking at this a little bit, what we found was running in real data centers, production load, busiest hour of the day, if we turned on TCP dump, it took away 7% of the entire server. I can't go to the people who run our data center and say, I have this measurement tool and I'd like to turn it on in production during the busiest hour of the day, and it costs 7%. That's a real short conversation. They say no. Right? Just can't use TCP dump, period. Too slow. If I come in and say 1%, they say sure. And somewhere in between, then it's a long, awkward conversation, which I hate to have. So this is the same diagram, same kind of diagram on a 16 processor machine, showing in time everything that's running on each CPU core. There's a little bit of thin black here and there of idle CPU cores, but mostly things are busy. I'm going to show you 4 slices of exactly the same data. So this is by CPU. This green and orange stuff is running along the top, and there's some idle, and there's some interrupt handling, there's some other stuff along the middle, and there's some stuff in a little red block along the bottom. This next piece is the same processing sorted not by CPU number, but by which remote procedure call it's executing. Which transaction, which search. Actually, these are, I think, updates. No, these are searches. So there's 40 searches shown in here across this time. This one starts a little later than the one above it, a little bit later, and they all take, in this case, about 50 microseconds, except for this guy and a few others that take like 10 times longer. And I'm the one who's interested in the 1%, the tail latency of why do those take 10 times longer? And if we look at the same data, this is the 23 locks that are being held by those 40 transactions. And these are the same execution sorted not by CPU number, not by transaction number, but sorted by software thread of which thread is running which search query when. And in this case, it turns out there's 47 different threads. And the little thin arcs are this guy blocked and is waiting on that lock. And later it wakes up again, and then it blocks again and is waiting on that lock. And if you think about, these are all the same scale. If you think about the normal execution is just a little bit of across the screen, a tenth or so. You see that these lock holding times are way too long. And that's the fundamental problem with this particular slice of data is the software lock holding times where the thing you wanted to finish can't finish because it's waiting on something else. It's waiting for like 6 transaction times before it can make a little progress. And that was the fundamental performance bug. But you know, that's a lot of big messy stuff. So I'm going to show you the same data, just highlighting the one guy that we're looking at that's slow. So it runs for a little bit. We're now back to CPUs. On CPU 9 for a little bit here, and a little bit there, a little bit there, and it's not running at all in between. Time is going. If you did a CPU profile of this transaction, you would learn nothing. Because CPU profiles don't tell you about the time when you're not running, which is the whole story with this transaction. It's why is it waiting? CPU profiles tell you what's going on when you're actually executing instructions. So that's the one RPC, and you can sort of see the surrounding context, which turns out to be useful, of course. Here's the lock it's waiting on. Oh, it's waiting on the same lock almost immediately again. So here it runs for a little bit, bam, waits on a lock. When, after a long time, gets dispatched again, runs for a little bit, bam, waits for the lock. Waits quite a while, finally gets dispatched again, bam, it's done. That's why it takes 10 times longer. But there's a really curious thing in here, which I'm going to show you on the next slide. This purple arc is the wake up from, this is the process running on this CPU that was holding the lock. And this is the instant at which it releases the lock, and the line up here that was the lock stops. And this process, when it releases the lock, part of the lock software locking mechanism says, oh, somebody else is waiting on you. Here's a list of all the people waiting. Go run one of them or more. And so this is the point at which the process that was holding the lock and released it wakes up the process that I care about. But it doesn't actually start executing for another 50 microseconds. So this is, I'm done, go run. This is the kernel scheduler finally gets around to running it. This 50 microseconds is longer than the normal execution time for these transactions. So I'm losing one complete time just in the wake up. And then it runs for much less than 50 microseconds and then blocks again. This is the futex call inside of Linux. How come it's waiting for 50 microseconds? Now, if we look at the context a little more carefully and put in the other things that are going on, kernel dispatcher decided at this wake up to run this other guy on the same CPU it was running on before, which turned out to be busy. Why would it say run on the same CPU you were running on before? One of your students back there needs to know the answer. Why would the Linux kernel dispatcher run a process that becomes ready on the same CPU core that was running on a little while ago? Affinity policies. The basic idea is, oh, if I run it on the same CPU it was running on before, all of its memory accesses will get cache hits. Oh, so that's good. So let's wait and then we'll run it and then life will be good. Except, how long should you wait? Oh, and incidentally, during that wait time, it turned out CPU 3 was idle. So we could have started sooner. So if you wait on a hyperthread, a CPU program counter that's sharing a physical core with another programmer, if you ran on the other program counter using the same caches, you should never wait if you're going to redispatch on the other of a pair of hyperthreads. If you're going to redispatch someplace that's sharing the L2 cache with you, for today's sizes, you could afford to wait, you could save up to about 10 microseconds by waiting and running on the core you're on. And if you're going to go to a core that doesn't share an L2 cache but shares an L3 cache, you could save approximately 100 microseconds. Or you could lose 100 microseconds by going to the other processor, and it takes a bunch of cache misses. And if you dispatch, if you have a multi-CPU chip, multi-socket processor board, and you go to the other socket, life is really slow because now everything is going out to main memory to get the data that was in the wrong chip. But 50 microseconds is large if you could have done an L1 cache or an L2 cache choice instead, and it's not a great amount of time to write even in the L3 cache case. So we really need something that pays a little more attention to this in a big environment. If you're running 4 spec benchmarks on your PC, none of this happens. None of this matters. Some of it happens. But to really understand what's going on in this complex environment, We need to do a lot more tracking of simultaneous transactions across the servers, across the cores, across the threads, across the queues, across the locks. The pictures I'm showing you, actually, when I looked back, they represent about 10 years of work off and on. The one Gmail picture was from 2004. And Google did not have the tools to be able to gather this data and draw pictures of it and see what's really going on. So it's taken a while. So just to summarize the second part about lots of transactions, things can hit thousands of servers, bam, 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 and get answers back and need to merge them. The slowest path dominates, so you need to pay a whole lot of attention to tail latency. And controlling the lock holding times is something as a software industry we're no good at, except in some of the very narrow real-time field, but not in arbitrary programmers write arbitrary programs that happen to run on the same machine. For instance, cloud servers, where you're selling time to various people and you have no idea, who's going to be doing what. And programmers who write stuff with lots of locks have very poor concepts of what's a reasonable holding time, what's an unreasonable holding time, and how badly you can get burnt. And then we really need smarter schedulers and smarter people to think about these issues. So that's the second section. Now I'm going to talk a bit about isolation between programs. So this is a time histogram of a disk server that I've worked on, showing how long it takes to do like a 64 kilobyte read from this disk server. This is a client machine over here, sends a message to a machine that's somewhere in the room, a quarter mile away or whatever, and says, read this block, and the disk server eventually says, here's your block. And a whole bunch of those requests come back, just looking at the disk server time and ignoring the network time, they come back in 0 milliseconds. That's because this peak is because our disk servers, stuff that they've read recently or stuff that's been written recently is sitting in RAM, in a RAM cache on the disk server, and the data's right there, and bam, you get it back. Then there's another peak here around 3 milliseconds. Now 3 is an odd number. About how long does it take a disk to go around once at 7,200 RPM? Yeah, it's 120 revolutions per second, so it's about 8.3 milliseconds to go around once. So this is less than half a revolution. How can you go to a disk server and say, give me stuff, and it doesn't have it in RAM, and it comes back in less than half a revolution? And there's a whole lot of them. And there's not any that are a quarter of a revolution or 3/4 of a revolution. These are hits on data that has passed under the read head recently, and the drive itself caches typically a track or two of everything that's gone by recently. And this is just the electronic connection time over the PCI Express bus and back to get the data that's been sitting there in RAM inside the drive. And that tends to hit, on the machines I was looking at, 3 milliseconds. And then there's a big hump here around 25 milliseconds, which is go to the disk, read a block, get it back. And then there's this long tail. And the 99th percentile latency in this was 696 milliseconds, I'm sorry. 0.7 of a second. So 99% of the accesses were down here and fairly good, and 1% are out here. More than half a second just to read a disk block. So, and these are all non-repeatable. You go read the same block again later, it's fine, it's fast. So when you look at non-repeatable tail latency, it essentially has to be coming from some kind of unknown interference. Something got in the way. And the problem is you don't know what it is that got in the way. If you knew what it was, you'd fix it. So when we look at isolation of programs where the same thing happens if some other program interferes with you and slows you down, if you can successfully isolate programs from each other so that they aren't interfering, then you get to reduce the tail latency, sometimes quite substantially. And if you can reduce the tail latency, you can actually load more work on a given server by substantial amounts. And if you can do more work on a given server, you'd need to buy fewer servers, and that turns out to be worth a lot of money. So even though it's sort of weird puzzles, it's something that any business sense company will certainly pay you to do. So most interference comes from software, but a little bit comes from hardware, and I'm going to talk for the rest of this isolation section on hardware underpinnings. We'll come back to the software in the last section. So some of you, I'm sure, have dealt with awkward neighbors in shared apartment buildings, but some of the hardware underpinning analogy would be living in an apartment that has particularly thin walls or bad kitchen venting, and your neighbors cook cabbage or whatever, and it's unpleasant. It interferes with your life. And if we look at some of the hardware that we share in servers, it's the same issue. We've got some shared resources that are not being shared very reasonably. So I'm going to go back to my 16 byte per cycle guide. I'm going to say, so what happens if CPU 0 is moving 16 bytes per cycle flat out? We were successful at that part. Let's look at what's happening in the caches. CPU 0 is here. CPU 0 is going bam, 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 and pretty soon all of the L1 cache for CPU 0 is full of CPU 0's data. And in fact, all of the L2 cache is full of CPU 0's data, and pretty much all of the L3 cache. And these other processors are getting hosed. The work on CPU 3 runs slowly because CPU 0 is filling the cache. This happens all the time in all of the machines you can buy today. You go to Google Cloud Server, and if somebody else, not you, is banging the cache, your program runs slowly, and because you're paying per hour or something, the amount of actual work you get in that hour is a lot lower. Same thing with Amazon or Microsoft or anything. This happens all the time in our data centers, where we tend to run 20 or 30 different unrelated programs on the same servers simultaneously, because otherwise we have idle time, and you hate to buy machines when you have idle time. Particularly the VP who's paying for them hates to do that. So this is a problem. We don't have, in our industry, we don't have cache isolation. One processor can completely ruin the performance of all of the others just by using the memory a lot. And I don't think there's any good software solution to this. There are some software half measures that involve partitioning the cache, and you get an eighth, and you get an eighth, and you get a fourth, but it's big granules. And you'd really like to reach the point over here. The desired idea is you'd like the L1 cache for CPU 0, 1, 2, and 3 to be approximately a fourth of the stuff in it is for CPU 0, and approximately a fourth for CPU 1, CPU 2, CPU 3. And the same thing at the next level, that approximately whatever the fair share is, an eighth or a 16th, is for each CPU. And I say approximately because you want some slop. If CPUs 1, 2, and 3 aren't doing anything, they're all running the idle loop, you want CPU 1 to be able to use some of the cache, but to give it up quickly. But you'd like to reach that sort of environment when there's actual contention. And this partitioning, like if you have an 8-way associative cache and you have 16 different contending threads, you can't give each of them a 16th. You can give 0 or an eighth, or 3/8 or 2/8 or whatever. The granularity is just no good. And if you give one process an eighth of an 8-way cache, you're really giving them a small one-way cache, a direct map cache. And you get all these second-order performance anomalies when two addresses happen to land on top of each other in the cache and thrash. So I'm a fan of selective allocation, which there are papers on starting in 2004, but has never been built. So it's not my idea, I just want to push it. That you give each thread or each CPU core a target cache size, and you just allocate lines freely as long as that CPU's use of the cache is underneath its target. If it's over the target, you bias the cache allocation so that it preferentially replaces its own cache lines, leaving the other guys alone. And then you allow some over-budget slops to avoid, if the other ones aren't in use, to avoid underutilization. So that looks like this. You give each CPU core two small counters, the order of 10 or 15 bits, one of which is the target of, this one gets 25 cache lines, this one gets 25, this one 25 out of 100. And this one is currently using 27, so it's over budget. This one's using 24, 24, 24. They're under budget. So the over budget guy, you say, when you take a miss and need something else in the cache, replace something that that CPU already owns, and don't replace the others. You do the same thing at the next level. You give each of them some target, and you have them preferentially replace their own. Now this costs a few bits per processor, which any chip vendor would do if they thought about this and were motivated. It also costs a few bits per cache line to say who owns it. Because if I replace a cache line from CPU 0 that had some data from CPU 1, I need to go and decrement CPU 1's counter saying you don't have this cache line anymore. Otherwise the counts are immediately all bogus. And so you need a handful of bits per cache line to keep track of which is the processor that touched it last. And so far, none of the chip vendors who've looked at all these papers have been willing to spend those bits. And so we get this one program with no isolation can ruin the performance of all the other programs. So I think this is an area where we actually need some hardware help. I'm going to skip over a few of the details. In particular, I'm going to skip over the improvement. So the underpinning on the isolation is you really need good fences make good neighbors. You need a way with some hardware support to keep program 1 from slowing down program 2. In all of the places that are shared throughout the hardware, and there's more of those than you might think, but if you make an explicit list, pretty soon one of your office mates or whatever will add something else to the list. Oh yeah, that's shared. The memory buses are shared. The TV entries are shared. On recent Intel processors, there's an instruction that generates a random number. But you can only do about 30,000 of those a second because there's actually some physics and stuff going on to get randomness. And that particular instruction, if you go bam, 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 looking for random numbers after about 30,000, suddenly the instruction takes a long time, a millisecond or so. So if my antagonistic bad neighbor program is generating random numbers way too fast, and my simple good neighbor program wants one random number, it waits an extra millisecond it wasn't expecting to wait. And if that's a real-time thing, that millisecond can be really expensive. So we need to isolate things. We need to pay more attention to shared CPU scheduling, shared caches, shared networks, shared disk, the whole works. And we need a lot of innovation in this area. These are far from the best ideas possible. And it's something that we'll be needing as an industry over the next 5 or 10 years. So I'm going to finish up fourth section on measurement underpinnings. I think some of you have used CPU profilers that take a sample of the program counter now and then and then draw this sort of scattershot picture of you were here, you were here, you were here, and you were here more often and here less often. And you get these little granular samples and you get some idea of what's going on, and it tells you a fair amount about the average performance. And you get a few blind spots. You never get to see the outliers. You never get to see the 10 times and 100 times slower things. You never get to see the 99th percentile slow things because they're averaged in with the 99 other fast things. So it's a good tool for telling you what's going on, and it is useless for telling you why. And of course, CPU sampling doesn't tell you anything about idle time. So this is actually Chuck closed, and the real painting is this. This is just a crude sample. This is the real painting. He makes little, wonderfully detailed pixels. He's actually somebody who has, I think, macular degeneration. He can't recognize people's faces except that he paints them and then he can recognize them. So if you do traces of everything that's happening time sequenced, you get all of this detail. Now you get to see what's going on in the outlier that's different. Unfortunately, the blind spot for that is you have to be really careful about the tracing overhead. If you're tracing 200,000 events per CPU core per second, you've got a lot of processing, and you only are allowed a 1% extra overhead. Otherwise, there's this hard conversation with the people who run the data centers. then you have much less than one cache miss time to record one event. And so you have to be very careful about blocking them up and using different cache lines for different CPUs as you're recording traces. But all that is doable. That's all just straightforward engineering. So I'm going to give you an example of this. So this is our histogram again, except now I've labeled the 7 peaks in this. There's the one at 0 we explained, the one at 2, the one at 3 we explained. And then there's these 4 peaks out here. There's one at 250 milliseconds, there's one at 500, there's one at 750, there's one at 1,000. What's odd about that? They're all multiples of a quarter second. What could possibly be causing an unusually large number of disk transactions, reads, to take exact multiples of a quarter second? Guesses? Energy savings. Wrong time scale. Energy savings can cost you 100 microseconds. Yeah. So each of you think of a guess, and you'll find you're all wrong. So this is a trace of 13 disks on a disk server. The reads are shown in blue. The reads actually at the disk are shown in blue. The writes are shown in red. The sort of diagonal black lines are showing the read time at the processor, and because of deliberate read ahead, the processor may return the answer before the read on the disk actually has finished. And there will be a bunch of writes that are buffered up in memory that don't touch disk at all. But over the course of 700 milliseconds on 13 disks, we get this sort of picture where the top disk isn't terribly busy and is doing reads here and there. And I have to ask you to ignore the red dots. They were unrelated, the magenta dots. And you see sort of ragged a bunch of reads and the occasional writes, and they're not correlated, and they're not 100% dense. They might be 50% dense. Okay, so that's normal. Here's the same 13 disks, the same server a little while later. And all the disks are busy, and then bam, there's this phase transition. All the disks do 2 or 3 reads, and then nothing happens for 250 milliseconds. And then they all do a few reads, and then nothing happens for 250 milliseconds. And in fact, the delay of something that came in just after this edge is 250 milliseconds. And the delay for all these guys is 250, 250, a little under 250, 250. And there's some that start here that are 500, and there's some further out that are 750. This goes on for 9 minutes. And then there's a phase transition, it goes back to normal. So what could be going on here? It has nothing to do with any individual disk. You know, if there were one disk that suddenly got slow, then that disk would be doing something weird here and the rest would be normal. It happens to all the disks simultaneously. So it's something that's shared, which means it's the CPU or the network, but it's not the disk. So all of the things that you might have guessed about, oh, the disk is doing extra revolutions or recalibrating, all that, can't be. But you don't know that until you do this trace of what's happening on every disk instead of just a sum or an average over the whole works. So what's actually going on? So when I saw this, I did a search of all of our source pool for 250 and 0.25 and a number of things, and I found no 250 milliseconds. And then I sent email to a whole lot of people, and 2 days later the answer came back. Oh, and the 9 minutes means that it's not some temporary thing. It has to be some kind of programming mistake, and there's something that happens to get you in and something that happens to get you out, and how long it is not actually relevant. So the answer came in, oh, the kernel was throttling the CPU because it's using more time than it bought using internal accounting. So this particular process, i.e. the disk server process, was using too much CPU time, and so the kernel, to protect all of the other programs running on that machine, the kernel says, oh, you're over your CPU allocation. What I will do is I will run none of your threads until a multiple of a quarter second, and then I will run all of your threads, And if they take too much CPU time, I will throttle you again and wait another quarter second. And the only way you get out of that is, by fluke, there's some quarter second where there aren't a lot of new requests. And then they stop throttling you, and bam, you're back to normal. This happened again, this is 7 in the morning, it happened again at 6 in the evening. And so another person started looking at our entire fleet and said, how often does this happen, now that we know what to look for? And he found it was happening on 25% of all of the disk servers worldwide within Google, for an average of about 30 minutes a day. And he found some machines where it was happening for 23 hours straight. And this is an environment where we like to give answers or searches back in 200 milliseconds, and this is 250 and up. And he also found it only happened on older, slower servers, which were fundamentally under-provisioned as far as the internal accounting, the pricing. So fixing that, it had been going on for 3 years. Fixing it paid for my salary for 10 years. The picture I showed you is the picture that caused it to be fixed. Nobody had ever looked at the traces. We take disk traces now and then. Nobody ever actually looked at them, drawn pictures of them to the point where you could see a pattern and thought about and investigated and found out what was causing it. So never attribute to malice that which is adequately explained by stupidity. Some of you may have come across in this industry. My corollary is never attribute to stupidity that which is adequately explained by software complexity. This is all done by layers and layers and layers of owned by different groups with different goals and different agendas. And this is normal in our industry. And so the thing to do is to work on understanding what to measure. All the performance mysteries in the world are simple once they're understood. But if it's a mystery, it means you don't know what's going on. And the way to approach that is not to do this guessing stuff. This is for the hard problems. This is not for the stuff that the CPU profile told you what was wrong, you go off and fix it all. I'm interested in the things that nobody fixed because they're too hard to understand. Okay, and for those, you really need to say, guessing is not a strategy. And in fact, software engineers are singularly inept at guessing what's going on in performance problems. And instead, you need to ask the question, what data do I need that would tell me what's going on? And then go work on gathering that data in some way, or some close approximation to it. And then you get to see what's really happening. And then most of these things I found are 20-minute fixes. It may take 2 months to understand what's going on and to end up with the right picture and then say, bam, here it is. And then they're all simple. But they're all different. There's no like magic, let's build a software tool that will discover performance mistakes. Programmers are much too creative. So you need low overhead tools. You need to be able to see all the dynamics, every transaction, every remote procedure call. You really need to timestamp everything that's going on and be able to do long traces. Long meaning like 30 seconds. 3 seconds is too short. 30 seconds is wonderful. 4 minutes you don't need. And to see everything that's going on. And then you can do pretty well. So just to summarize, we've got big data movement, big and small is different. Thousands of real-time transactions is a bit different compared to desktops. Isolation between programs is a bit different, and needing to do careful measurements is a bit different. Here's a few references. I think the copies of the slides will be available along with the talk. My first reference is to Shannon's paper. Because I'm a believer in you should go back as a computer science professional, you should go back and read some of the fundamental papers every few years. I go back and read Shannon about every 5 years, same paper. And I learn something new every time. Other than that, it's unrelated to the talk. There's a paper I did that I found a reference to 20 years ago about the memory. It's still the memory. Here's a couple references on the quality of service cache sharing ideas. And a few references on, I didn't talk about the Zcache, but this is sort of the next level of detail. Luis Arioso, I'm sorry, this is the wrong one. This is about Dapper, public paper about part of our internal tracing structure that does the remote procedure call trees and timestamps things. And there's a bit about fine-grained cache partitioning. Louise and Urs have written quite a good, it's almost a book, but it's available online as a PDF that I encourage you to look at about the data center computer as an introduction to the design of warehouse scale machines. The second edition, they really walk through Google data centers and the kinds of considerations for building them. So now I'll stop and take some questions. Anybody?
Yeah, sure. So the traces you were showing for that transaction, that was for one transaction in isolation. What happens if you're running like a real workload with, say, 50, 100 transactions concurrently running on that same set of hardware? How do they interleave? How is throughput? I'd be real interested in looking at a curve of throughput versus number of concurrent transactions.
Yeah. So this, we're getting there. Oops, one too far. So the CPUs, top CPUs all busy here, those are doing 40 different transactions that are all overlapped in that 600 microseconds.
Okay.
That's the kind of thing that's going on.
That's a 40 transaction one.
Those are the 40 transactions, and if you were patient, you could take that piece and find it up here. You could take that piece of execution and find it there, etc. So they're all interleaved on the CPUs. And on the software threads, they're all interleaved. And on the locking, they're all, you know, they're not interleaved on a given lock, but on individual locks, there's lots going on. Another question back here.
So when somebody comes to you and says, Dick, we have a long tail query, where do you get the intuition on where to start and how to start this kind of profiling? How do you know to blame hardware versus software? Or is that just something that you start iterating with tools and that's why the process takes a while? This conclusion is so specific, and you say it's the result of 10 years of work. So
the 10 years of work is building the tools that draw these pictures. The work on a particular, you know, Gmail is slow, what's going on is much shorter.
Sure.
I don't know. I literally start by saying, what information do I need to answer the question? And if things are slow, the thing you want to know is, where did all the time go? And if you do these profiles, histogram averages, you don't learn where all the time went. You just learn that the average uninteresting transaction does this. And so I'm a very strong fan of building slowly, methodically, very low overhead tracing tools that trace every event. The disk trace, the time scale is sort of millisecond. The CPU traces of kernel calls and stuff, the time scale is more like 100 nanoseconds per event. And what you need for a long trace of everything that's going on is you need the software hooks to write things down as you go. And you need on the order of 16 bits to say what happened, what event. And you need on the order of 16 bits of timestamp to say when. And you need to factor out all the high order bits, otherwise you're spending too much time. So you need about 4 bytes per event. And you say, well, I don't know, if there's 200,000 events per CPU doing kernel calls and back, and you've got 16 CPUs, you know, then you've got 3.2 million events per second or something, and at 4 bytes each, and so it's about 12 megabytes per second. You'd say, okay, that's a manageable amount of memory bandwidth for doing the writing without interfering, but you need some place to put it, and you have to figure out, you know, how many. If you need 30 seconds of that, then you need at least 360 megabytes of RAM somewhere to put stuff into, but you don't need 300 gigabytes of RAM to put stuff into. And then you need to go build the trace stuff and then build some stuff that'll write, in this case, PostScript pictures or whatever, and then you look at them. The human eyeball is still by far the best pattern recognizer in the world. And I work really hard to put 250,000 data points on a single sheet of paper because I get much higher resolution on paper than I get on screens. And then I look at it. And, you know, when that picture came off the printer of the 250 millisecond delays across all of the disks, I could see exactly what the problem was that nobody had understood for 3 years. They could see that it was happening now and then. Okay, next question.
Three of your topics concluded with, we need the hardware manufacturers to do something. And I'm wondering what the economics are. I would think that data centers like Google and Facebook and Microsoft, et cetera, can provide a pretty large fraction of the server processor manufacturer's business. What's the economics that's not pushing them to give you what you need here? And I would imagine your needs at Google are not that different than the other data center.
I think that might be true, but I don't know. The answer to your question is 160 million PCs per year.
So it's
That's the design
still
target.
the case that
Okay,
that dominates?
and so my supposition, my hypothesis to you all is, as the industry bifurcates into cell phones and data centers, and the middle drops out, we will need to pay more attention to what's going on in data centers, and this is one early step to get you all to think about it. Yep.
So.
I'll take about 3 more questions and then we'll stop.
Individual servers have gotten too big. There's too much going on in one box.
Uh-huh.
Thoughts on
Fair
that?
hypothesis.
Huh?
Fair hypothesis.
Yeah, which is, I think, a result of basically Moore's law having you in another dimension.
No.
Particularly faster than data.
So there's a bunch of papers about tiny computers.
Go ahead. Should we be, instead of trying to make these big servers work better as big servers, would it maybe be better to have lots of little servers that don't have some of these inherent complexities that are very hard to deal with?
No.
Okay. Cool. Let me watch.
If you have lots of little computers, like little ARM processors, 32-bit processors, they can't address enough memory. So they can only do little pieces of little problems. They can't do good-sized pieces of big problems. They're difficult to coordinate when you have, really huge numbers of them. And they can't do much. You can't, with a puny processor, keep a 10 gigabit per second network link busy. You don't have enough CPU cycles to shovel the bytes out. So there's sort of a minimum underpinning to be able to do fast work at all. And I don't claim that we're in the sweet spot of what we can buy today in the industry, but I'm real sure that lots of little tiny processors, a tenth as fast as today's, is a bad idea because you just don't get to share enough. I mean, the nice thing about having a couple hundred gigabytes of RAM is you can have several programs share that. If you have 4 gigabytes of RAM and just one program and a puny processor, and you buy 1 million of those and you look over the fleet by some senior VP who's paying for them and sees that 80% of the RAM is unused because you've had to break stuff up into little pieces that aren't exactly the right size, that's inefficient. It's expensive. Yeah.
Are there any companies out there, large or small, that you see that are addressing this hardware issue?
No, I'm hoping some of you do over the next 5 years. I mean, these slides are about 3 weeks old. You had a question back here somewhere? Okay, one last question, last 2 questions.
So one question I've got is, how much of your data movement workload could be dealt with by adopting zero-copy protocols and pushing things down into DMA engines?
Yes, 0.
0?
Okay, here's why. I've watched this zero-copy DMA. Let me do the zero-copy network thing first. Every year there's this hand wave that says, oh, we can rearrange the kernel and do zero-copy network transfers. And they do not happen. They do not happen because if I hold a bunch of stuff that I want to send over the network and I'm the disk server software, and I can't hand it off to the kernel and the kernel owns it, and I say send this, I have to hold on to the RAM until it actually goes across the wire. If the wire is blockaded, what happens is the disk server piles up more and more stuff to be sent that hasn't been sent and runs out of memory and crashes. This is real. I see this happen. The disk server runs out of memory and crashes. By copying the data to the kernel and changing the ownership to the kernel owns it, the disk server never crashes. The kernel actually knows, and the kernel knows and the disk server doesn't, that the network is bottlenecked. And the kernel has all these wonderful mechanisms for queuing stuff and delaying stuff, and it's clean ownership issues. And so I've watched the deployments of kernels that do this within the company, and they always fail. And they don't get deployed past the first dozen machines. So it just doesn't happen. Okay, the DMA engine if I could get a CPU that can move 16 bytes per cycle, why would I want to take out a lock, share a single piece of hardware across 16 CPU cores that's a DMA engine, spend a while cranking it up, getting it going, go wait, somehow get an interrupt or a signal back saying it's done finally, unpack all of the stuff and free up the data structures that were describing what's going on, and then pick up the work again. I mean, Seymour Cray showed this with the 7600. He had a move instruction that would move from large core memory to small core memory, and it locked out the entire machine while it was doing the move.
Right, so edge caches wind up using this stuff a lot, right? Amazon's got a ton of them. And the question is why in your workload is this not working?
I don't know the answer to that. But I think that this whole DMA engine hand wave is not a good way to go. If instead you could put the design effort into having all the CPUs able to move data faster, it's a much simpler programming issue. Let me take the last couple questions and then we'll go on to the reception soon. You had one.
Yeah, so where I work, I can get the traces of the granularity that would be good for this kind of work. And I can see the long tails in the traces. My problem is that it's very difficult to actually make the pretty pictures that you can actually use this to explain to other people and figure out things yourself.
Okay.
So are any of these tools available?
No. They're not available partly because Google pays me to do this for Google. They're not available partly because in general there's not a lot of interest in tools that can handle 100 megabytes of trace input. You know, it's just the wrong scale for lots and lots of people. And the people who would be interested tend to be direct competitors. You had the last question.
So some of the challenges that you address, don't they emanate from the fact that you want to build your data center or supercomputer using generic processors like Intel or Sandy Bridge or ISIL?
Sure. We buy the cheapest hardware we can get. We're not a hardware vendor. And we would rather buy 3 PCs instead of one expensive, super high reliability something or other, because with 3 PCs we can have 1 or 2 of them fail and still get more work done for the same number of dollars. So the economics are strongly favored by commodity products. Good. Thank you all very much. Lots of interactions, lots of congestion, lots of different agendas. The whole works. So I'm going to talk about 4 areas where I think data center computers are different from desktops. Moving data, big and small. We find something on the order of 1/4 of all of our server time is spent moving data, memcopy, or Sterland, just finding the end of the length of a string of data, or send message and receive message, which are really have an embedded copy inside of them, moving data from network out of the kernel and into the user or whatever. So I'm going to talk a lot of the time about moving data, and then some about what's really going on when you've got thousands of transactions per second and how that's different from running 2 desktop programs. Talk a little bit about isolation between programs. This is an area where we actually need more hardware help in the industry. And then one of my favorite things, talking about measurement underpinnings. So here's data, big and small. In our servers, we're moving data from disk to RAM, from network to RAM, from SSD to RAM, and also a whole lot of just physically putting pieces of data together, juxtaposition. And some of that is bulk data, you know, send a megabyte here and there. But some of it is just little short variable length items. We store Unicode in the UTF-8 encoding, which is a variable length encoding covering all the alphabets in Unicode. And there's some 1-byte characters, and 2 bytes, and 3 bytes, and 4 byte. And you also need some 16-byte registers, but everybody has those. And if you look at today's sort of processor speeds at 3 gigahertz per second, times 16, you're up to 50 gigabytes per second of read traffic, and another 50 gigabytes per second of write traffic. And that means you need to be hitting the first level caches with a total of 100 gigabytes per second every cycle, all the time, every second for many seconds in a row. And if you mess up, and in fact, if you buy any of today's machines, you're actually talking 150 gigabytes per second because the stream that you're writing, every cache line is actually read first, completely overwritten, so the read is a total waste of time, and then written back to RAM. So there's a factor 1.5 loss in data movement in every processor chip you can buy today, which is unfortunate from my point of view. So here's a little bit on short strings where we're doing packet pieces or words or web pages or things. So there's just lots of little pieces. And I think I skipped a slide there. Excuse me a second. There, okay. And if you look at things like that in 16-byte chunks, if we want to move short stuff at the rate of about 16 bytes per cycle, that means you need to pick up most of 16 bytes, and on the very next cycle, the next chunk, and on the very next cycle, the next chunk. And if you look at something like the memcopy code, it spends a whole bunch of time up front trying to figure out what to do and what the length is and stuff, and you don't get. So it's fun to be here for the Distinguished Alumni series. The Alumni office claims you the first day you put your foot on campus. My dad is 95 and has Alzheimer's, and he doesn't know where North Carolina is anymore, but he still has his sense of humor. So I told him I was invited to give this Distinguished Alumni lecture, and without missing a beat, he smirked at me and he said, "So who are you replacing?" So this is a engineering talk, even though this isn't an engineering campus, so I brought my engineer's hat. And I'm going to talk about data center computers. My reading is that the industry is starting to bifurcate, and there's cell phones and there's data centers, and the stuff in the middle is going to drop out a lot. And I want to tell you a bit about data center computers and how they differ quite a bit from desktops. And I want to try to draw some vivid pictures of computing in data centers and expose some ongoing research problems and perhaps inspire some of the students here to contribute in this area, because I think it's going to be pretty important for a while. I want to mention in passing, it was really hard to find a picture of a woman with a light bulb instead of a man. So a little analogy, here's a California ranch house and an apartment building. The analogy is those relate to each other about the same way that a desktop computer relates to what? Data center. Lots of share. It means you want to use it. You want to put stuff into it and you want to get stuff out of it. And we will see in a little while what that means is caches don't work because you've got way too much RAM compared to the cache sizes. So this is a sort of an odd environment. I'm going to go through a little bit of a hypothetical cache structure and then go through some of the problems. So just quickly, this is, pretend you've got a 64-core machine, which is 16 physical cores, each of which has like 4 PCs, so hyper-threaded, whatever. And that each of the physical cores has its own level 1 cache, and a bunch of those, maybe 4 of those, share a level 2 cache, and all of them share something like a level 3 cache, and then there's a bunch of DRAMs. So this is sort of a generalization of the kinds of things you can actually buy today. And I'm going to take, as a forcing function, I'm going to talk about this forcing function for about the next 10 or 12 minutes. If I wanted to move 16 bytes every cycle, because 25% of my time is doing that, what are the real consequences? What does that mean for the hardware design? That one simple phrase, 16 bytes every cycle, if you take it as an honest statement, what it is you have to build. And I was astounded when I went through what you have to build. First, you need to have something in a load store kind of machine where you load 16 bytes and store 16 bytes and test if you're done and do a conditional branch every cycle. So just for starters, you need a 4-way issue machine in order to hit the goal. And when you're putting those together, you're moving little tiny bits of data, And it's really bad if you have to do like this four-way branch that says, go here and move 1 byte, go here, move 2 bytes, move here, because the branches, the conditional branches are always slowing you down. Or you're putting together packets and there's, you know, this header and that header and this VLAN tag and this other stuff and this checksum, and it's all physically put it together and then send it. We also do a lot of compressing and decompressing, and there's lots of data movement involved in those, and the decompressing is fundamentally picking up little pieces of a big file and putting them back together in the order they started out in. And then we do checksumming. Everything we write on disk is checksummed in software in addition to all of the hardware stuff, because otherwise we lose data. And so we're just taking passes over stuff. I looked at one of our disk servers and counted, and to read a block off disk, every byte of that block was actually touched in memory 11 times. So processors, the 4004 had no memory. More recent things like the Intel i7 have, you know, like 12 megabytes of cache on them. But when you look at a data center server, it's really this big dinosaur where everything is memory, and then there's a little bit of processor. And the connection between them is pretty puny. And if you look at where the money goes, the money doesn't go into the processor chip. It goes into lots and lots of RAM. 64 gigabytes, even up to a terabyte. You're talking massive amounts of RAM, which has a strong consequence. If you have a lot of RAM and you actually paid for it,